about which I wanted to talk was Markov chain Monte Carlo methods. And this was actually a presentation that I gave last summer at the System Dynamics conference, which aspired to be a sort of informal introduction to use of MCMC together with System Dynamics models. And if people were interested, I could show you in R, at a mechanical level, how this is performed. But it's more of a gentle introduction conceptually to why it's needed, and give some flavor as to the types of findings that can result from it. Thank you very much, Winchell. Much appreciated. So this is joint work like the stuff yesterday on particle filtering with Jushin Liu from Math and Stats. So many of you in the room who have taken my course are familiar with the notion of calibration of dynamic models. And I've long sort of referred to this as a matter of, as it were, triangulating a model from diverse data sources. The idea is that, often there are certain parameters where we have less information than we'd like, or we have multiple types of information, and yet we have other data concerning emergent behavior of the system that can't be reduced to data about one specific parameter. Rather, it speaks to the behavior of the model as a whole, but surely it tells us something about what plausible parameter values are likely to be. It often points us, it sort of constrains our possible guesses as to various parameter values if we assume the correctness of the basic model structure that we're using. There's only so many values that the parameters could be to explain the emergent patterns we see. So it provides some constraints. And those of you who have been through my class knows that calibration in its most basic form involves tuning values of less well-known parameters such that the model best matches certain observations. So we perform an optimization process where we tweak values of less well-known parameters until we get sort of the best match of the model against the data sources. And often we're matching multiple data sources at once, and we often formulate some sort of discrepancy metric, some sort of metric that represents how bad a given model fit is, and we try to minimize that discrepancy metric. And as many of you know, and logic and Vensim include mechanisms for doing this. And often there's a lot of learning that takes place from that that's very valuable. But there's some limitations to the process. Often calibration gives you back point estimates of parameter values, particular estimates for the best set of parameter values, but it doesn't really tell you how numerous those are, how unique those are. It doesn't tell you whether there may be other runners-up that may be very close to this. Maybe you're in some, broad valley at the end where just about any parameter value will do, and maybe there's many such values. And many packages, optimization will give you confidence intervals or covariance estimates associated with those final values, which give you some indication with confidence limits as to sort of how precise it is. But even so, it doesn't really capture multiple modes of a distribution. There may be things that are just about as good far away from you now, and they're outside your sort of narrow confidence intervals around this particular local minimum. So for that reason, I was motivated to look to computational statistics techniques to try to shed light on methods that would give additional understanding as to what the distribution of possible values are for parameters. And to examine this, we made use of, as a sort of thought piece model, we made use of some synthetic empirical data, which was actually produced by a known process. We actually know the ground truth behind this. And in an SEIR model, where we have the classic forms that you folks will have seen in my classes associated with it. So this is a standard match action random mixing representation of infection transmission, where we have a susceptible compartment. People get infected through exposure to infectives. And excuse me, this should have an E in it as well. S plus E plus I plus R in the denominator there. And then they continue on to the exposed category following infection. Following some incubation period, they become infectious and can pass it to others, and then they recover with some meantime healing. Fairly straightforward and fairly well known. And we assume here that there's some known fraction P of infectives that are reported, and we're going to assume, for the sake of this model examination, that beta, tau, and mu is time constants associated with recovery, time constants associated with latency, and this constant associated beta associated with transmission, the transmittivity, that those are known. Okay, so there's going to be some true underlying values, and then the actual values reported are some fraction of that, as drawn from a binomial distribution. Okay, so we're going to try to estimate here a value for C, this mixing coefficient, so contacts per person per day, and a value for P. And we could use calibration to try to arrive at these values, P being the sort of fraction of cases on average that are reported. We could try using calibration to estimate this, and we could get out point estimates. Potentially, we could get out confidence intervals. The shortcomings of these are that there's limited sense of variability. There's this assumptions of unimodality, or at least multimodal. You don't get a lot of multimodal insights more globally into what other values might do a good job matching the data. There's error weighting assumptions. For example, using least squares imposes some assumed distribution of errors between what your model would predict and what the empirical data actually obtains. That can be fairly heavyweight assumptions, and essentially by assuming this error metric, you are implicitly imposing this assumption concerning the distributional properties. And finally, you're assuming a single dynamic model in doing this, in undertaking this whole process, rather than thinking about a distribution of possible model structures. So here we're seeking a method that provides us a distribution of possible parameter values, a distribution that's known in Bayesian approaches as a posterior distribution, that takes some initial guess as to the distribution, a so-called prior distribution, and then in some sense learns from the empirical data and arrives at an updated estimate in the form of a distribution over parameter values. It's called the posterior distribution. And it specifies the probability density, or the relative probability density of parameters in light of observed data, one or more models under consideration. We don't go into talking about more advanced methods here, which allow you to take a probability distribution over models, but that is possible if you know what you're doing. It's fairly straightforward if your models differ only in their structure and not in the number of parameters. If they differ in numbers of parameters, there's more sophisticated approaches like reverse jump Monte Carlo methods that are able to take that into account, but it's a more sophisticated undertaking. But you can create distributions over models. And you can get out distributions over models that say this model is more likely than that one. And fundamentally, you're getting out this distribution over parameter values that are helpful in terms of assessing how broad is our distribution, or how specifically does our data point us to values. Now, once you get this posterior distribution and the ability to sample from it, we can derive many things. We can arrive at point estimates, such as mean values or maximum likelihood estimates or minimum variance estimates, etc., for parameter values. We could take these samples, for example, and take their mean for 1,000 samples, and we'll get a pretty good estimate of the mean of the distribution. We can take these samples and we could assess their dispersion through standard deviation or other measures. We could take these samples and try to find the maximum of them to find a most likely estimate, given a flat prior in that case. We can also ask questions, what's the likelihood or what's the probability that intervention A is better than intervention B? We can arrive at credibility intervals for diverse model output, including how much A is better than B. And we can provide visualizations of parameter space. These things are notable limitations back here. If we were to look at what we get out of a calibration routine, we actually we have a difficult time mapping estimates of confidence intervals over parameters to confidence intervals over differences between intervention A and intervention B, or confidence intervals over model output. You can't just map directly. You can't say, well, the confidence is upward 95% here. If you apply, if you pass it through the model and take the model output for that, it corresponds to the upper 95% for the output. It doesn't work that way. You can't go directly from a confidence interval about parameters to a confidence interval about output or difference between interventions, whereas this is very straightforward to do from samples of the distribution. So if you can arrive at the ability to sample a distribution, that's what we're going to be showing you how, you can do a lot of useful things with it. You could say, the likelihood of this intervention is better than that one. You could say, what's the estimated give me a distribution over the cost difference between this intervention and that intervention, or the difference in quality adjusted life years saved, or what have you, in a very straightforward way, and get credibility intervals over those. So it's a very useful thing to be able to sample from this distribution. I don't spend a lot of time talking about it, but it's useful. So, for example, in our work, we work with Jushin and Yu, we regularly see distributions that look something like this. And this is not a type of distribution that's not well described by a covariance matrix, nor by unimodal description. So the darker areas here are the peaks of the distribution, and what this is telling us is that, in terms of combinations of C and P, you can either have a larger C, but in that case you'd have to posit a quite low P, or you could have a high P and quite low C. But in between, there's not much chance of this occurring. Really, the weight of the distribution lies out here in these sort of areas. So again, this is a multimodal distribution that's really not well described, even if your calibration routine returns confidence intervals or measures of covariance. Okay, so for this presentation, we're going to try to use some of the notation that's familiar with MCMC, in part because if you go to the MCMC literature, you'll see this notation used almost universally. And if you're not familiar with it, you'll think, well, it's just a bunch of Greek letters, I don't know what they mean. But it's used in a very particular way, and I'd like to introduce you to that. It will afford us an economy of presentation here, but also make it less daunting to go into that literature and look at other examples where people have applied similar techniques. So we're going to use this Greek letter theta to represent a vector of parameter values. in this case, it's a 2-vector. It's a pair of values, one for a particular value of C, one for a particular value of P, and you can imagine, values of theta where C is higher and P is lower, or where C is lower and P is higher. Those are all different values of theta, and so theta is going to be in this C versus P vector space. So that's what we're going to denote by theta. In general, theta is going to consist of a series of parameters for the model, and if you're trying to apply this to choose models, one of them might be a parameter, a discrete parameter that indicates model 1, model 2, model 3, model 4, for example. Notable thing here, C is right now an element of this underlying model. It's an element of this model. C appears in here. P actually does not appear right in this model. It actually is it's an element of a probabilistic model that says, okay, if you have a certain level of infectivity in your model, what's the likelihood, or how many people actually get reported? So it's actually not a member of the dynamic model. It's a member of a probabilistic model that accompanies that dynamic model. And that's notable. So C is something which is actually in the Venn model. P isn't at a very concrete level. And then we have this observed data, and we give it the name Y. Now, in this case, Y is a time series of estimates. It doesn't need to be. It can be one value. It could include many different time series. But it's a collection of data points, of observations, of empirical data that we're trying to get this system dynamics model to match. Okay. Okay. So, what's this Markov chain Monte Carlo stuff? Well, fundamentally, it's a way of helping us to sample from, to draw values from a distribution over parameters. Okay, and where the likelihood of drawing a given parameter value, given value for theta, is proportional to the likelihood that the model with that value of parameters, could explain the observed data. So it's a principled way of generating samples from theta according to a posterior distribution, where this posterior distribution assesses the likelihood of having that model produce that sort of empirical data. I'm using likelihood in a loose sense there on the probability density of producing. Now these samples from the posterior distribution are generated over and over and over again. So we actually sample from it again and again and again and again to arrive at a large set of samples. Why? Because we want to be able to take their mean, or we want to be able to take their credibility intervals, or we want to be able to take the median, or we want to be able to establish the mode, or what have you. So we want to accumulate a broad set of these samples. So we have to draw them again and again and again. So we call it Monte Carlo. Okay, for each such sample, we can do very useful things with it. We can accumulate statistics on it. We can derive model outputs for that sample that correspond to that sample, and derive at distributions over them, etc. We could calculate intervention gains for those assumptions of C and P. How much better is this intervention than that one, or what's the difference between them, the differential between them? Now, we've explained the Monte Carlo. We're drawing these samples again and again and again and again. What's this Markov chain stuff? Well, the Markov chain is used to generate the samples. It lies behind the scenes. You actually don't represent, you don't build the Markov chain in an explicit sense. It's not reified, but it's implicit. And it lies behind the scenes. It allows you to generate these samples. Okay? So it's not like you have to create an instance of Markov chain class. You don't see it. It's implied by the basic algorithm. Okay. So let's talk about the high-level operation of MCMC for parameter estimation in this case. what do you have to specify for this? I mean, what do you have to bring to the table to apply this approach? Well, there's a couple of things. There's three major ones. One thing is you have to assign, to do this in a Bayesian way, you have to assign prior distributions. So you assign some distributions that encode your perhaps subjective likelihood of seeing different possible values for C and P. Maybe you have some basis for it, you can base it on that, but maybe you're just sort of guesstimating it with some sort of expert judgment or with your own guesses. And sometimes you have a flat distribution. A uniform distribution is a common non-informative prior. So you can have these prior distributions. You have to formulate, this is probably the most tricky part of it. It's not terribly difficult, but it requires thinking. You have to formulate what's called a likelihood function, a likelihood formula that indicates how likely it is that you would have seen certain empirical data if you had a value of, in this case, C and P, particular value of C and P. Now, the key thing that you have to realize here is to formulate this likelihood function. To ask how likely is it that we would have seen this set of data in red given this model with certain values of C and P and with known values of these guys, beta, tau, and mu. In order to assess that, to say how likely it is we would see the red, we're going to have to do something. I mean, if you told me right now, you said, how likely is it we see this output with a certain value of C and P? I'd say, you know, I don't know. To answer that question, I need to run the model. I need to run the model. I need to run it on that particular value of C, right, at the least, to get some number of infectives over time. And then, if I had a number of infectives over time, then I can tell you how likely it is that that value of P would produce these red marks, these red points, the empirical data. Without the ability to run the model, I'd have a very hard time assessing the likelihood. And that's exactly the point here about the integration of these methods with simulation models. So here, our likelihood function is going to be operating on, it's going to be asking how likely it is that we would produce the empirical data Y, given not just theta, but critically. And if you remember one thing from this whole presentation, it would be this. It's not just from the value of these parameters directly, but from the simulation model output that results from the value of those parameters. Okay? So we're saying how likely it is that we would see these red outputs. I could plug in the value of C right into there, and I could run that model. How likely is that I'd see this output? To consider that, I need to typically consider the output of this model, in this case, the number of infectives over time. If I knew that, then I could say how likely it is that I see this data. Okay? So in our case, in the case of performing MCMC with simulation models, we want to be considering the output of the simulation, and that's part of our likelihood. So our likelihood is going to be operating, in this case, it's going to be a likelihood function that has recourse to, has the luxury of accessing data, not only about the parameter values themselves, but also about the simulation model output. Okay? That's going to make it a lot easier. The simulation models are a friend, as I hope simulation models are in general, your friends. And in this case, it's going to be a key asset, a key ally in computing this likelihood function. Okay, so those are two things: prior distribution, this sort of subjective likelihood of different values. To be honest, in this case, we assumed a uniform distribution because we didn't have any particular thing, but it's uniform between. Uniforms always have to be bounded. I mean, it's uniform distribution has to integrate up to 1, so it has to be bounded, and in this case, it was uniform. P couldn't go above 1, for example, couldn't go below 0. So those are two things: the prior, the likelihood function. The likelihood is the hardest part of doing this. at a formulation level. Finally, there's an application of Bayes' rule, and this is normally just goes on behind the scenes. You don't have to even pay attention to get a rule for the posterior in light of the prior and the likelihood. So the posterior distribution here, if we have, some of you may remember this, if we have a likelihood function, which basically says how likely it is we would have observed this empirical data, those red points, in light of theta, and implied here is sort of the model output on theta. This is sort of the model, simulation model output that you're interested in, of various sorts that is used here. This is the likelihood function, and the posterior probability will actually be, we want to flip that around. We want to have probability of theta, probably density of that C is a certain value and theta and P is an additional value. What's the relative likelihood of that and some other value of C and P? Given that, we can formulate that simply as this one here, the likelihood, times this prior, and it's times some coefficient. So we typically don't say equals, we say it's proportional to that. Y, well, it's Bayes' rule. If you put this over P of Y, then it'll be exactly equal to it. And in this case, it's just proportional with some constant that doesn't change based on theta. So basically, if we have these two pieces, the prior distribution and the likelihood function, we can multiply them and get something that's proportional to the posterior. And that's all we need. That's all we need to perform this. And so this last piece, applying Bayes' rule, that goes along with this. Okay, so then what happens? Well, a Markov chain is going to be used to generate samples from theta with a distribution that's proportional to a posterior distribution. And for each such sample, we can do things like accumulate statistics, accumulate the mean, accumulate the median, compute the median, or what have you. Okay, so let's talk about each of these pieces. Prior distributions. We often have some sense as to where things lie ahead of time, and sometimes you would form a minimally informative prior, such as a uniform. Sometimes you say, no, I want to assume that C is normally distributed around some value, maybe because you have information from the literature that suggests it varies. Maybe you have data from, Anderson and May book, dynamics of infectious diseases in humans, and you want to, on the basis of that, assume a normally distributed prior. You could assume a non-normally distributed prior. Whatever distribution you want to put in there is fine. Sometimes we throw in a minimally informative one, such as uniform. Some people do use Mcmc in a non-Bayesian way by not using a prior, and that's also possible. So in this case, we have this theta, this sort of parameter vector. We're trying to assess a distribution, a joint distribution over theta. And we're going to have a prior associated with this. We're going to actually examine two priors, just as a teaching moment. One is going to be an uninformative prior. It's going to be 1 over 50 for this range, and 0. Otherwise, 50 was an upper range, extreme upper range, and what I thought C could be. 0 is minimum. It doesn't make sense to talk about negative contacts per day between people. And P at a range, it's a probability, so it's between 0 and 1. And so I impose this minimally informative prior. The other thing I did, though, is I threw this a curveball. I deliberately challenged it. I gave it a very misleading prior. I gave it a prior that's just way off from its actual distribution. It was pretty firm, saying it was pretty peaked. It was pretty firm in sort of saying that it was probably lay in this area that was quite far off. Okay. So it's on priors, and we're going to see how it performs against both of these priors. Okay, how well does it hold up to a really badly chosen prior? Okay, the next thing is the likelihood function. We're going to have to formulate this likelihood function. This guy here tells us how likely it is we see the observed data, y, in light of these parameter values, theta. By implication, also assuming the model. So we have to specify this is a key part of what we're doing, probably the key part we bring to the table besides the model itself. And it's going to be central to assessing the relative likelihood that different parameter values have, different parameter vectors have. So we really want to treat it carefully. So what we did in this case, and it's subject to critique, what we did in this case is we assumed, okay, at each point, reporting point, at each of these points back here, each point, week, I guess this is every 10 days, yeah? So every 10 days we had a reported data point. We assumed that for each of those 10 days, there was a binomial draw with some unknown probability p. That's one of the things we're trying to identify. That's an element of our vector here. With probability p, infectives were reported. And so if we have a certain number of infectives in the underlying system at time 10 or time 20 or time 30, time 0 for that matter, the likelihood of observing this number of extra reported cases is distributed according to a binomial distribution with this many flips of the coin, and it's a weighted coin, and this chance that the coin will turn out heads. Okay, so in other words, 4 times, say, 30, right? We ask, okay, this many people who are truly ill out there, as predicted by the simulation model, each of them has this probability p of being discovered. So we're going to flip our coin 30 times. Just like that. And we're going to get out some number of reported cases. We're going to assume that y is generated by a process like that. Each person has an independent chance of being detected or not according to probability p. And p represents sort of the overall chance someone gets discovered. Okay? So that's for a given point in time, we assume that this given chance, this number of reported cases is distributed binomially with this many draws, I sub 10i, and with each having a probability p. And then we assume that each of the time points is independent in terms of its probability. And so we simply take those probabilities and we multiply them out for each successive data point. So maybe we have, in our case, our model has probability 0.1 of predicting the empirical observations, the empirical data point y sub 0, based on the number of actual infectives posited at that time, I sub 0 and p, and then at time 10 we have a probability of 0.2 of the model's posited number of infectives predicting the number of reported cases there. And so to this point, pi for the first 2 data points, 0.1 times 0.2 or 0.02. And so on, and we just sort of multiply those out. So that's our likelihood function. That's this function here. And you see how it makes use of f here. This is the simulation model results. Simulation model results for parameters theta, right? In this case, it's for c. So we see how it's made use. I mean, that's what I is. Where did I come from? I comes from no less than the simulation model. Eh? Okay. Okay, so that was our likelihood function, and now we apply Bayes' rule. Boom. So we have this, and I talked with you about Bayes' rule there, and the point here, the key point here is that P of y doesn't depend on theta. No matter what value of theta is, P of y is the same. So if all we care about is the relative value of the posterior parameter, which is all we need for Mcmc, we can ignore P of y, and all we can simply say, we could just, on a relative level, we can compute the posterior by multiplying the likelihood function times the prior. Boom, done. That's it. That gives us something proportional to the posterior. And P of y doesn't change with different theta. So we're just interested in changing different thetas and finding the one with the best posterior. We don't have to worry about y. The best value of this over different thetas of this thing down here on the right, it occurs at the same theta, which maximizes that thing in the upper left, right there. That includes the colored numerator of the denominator. So as long as we have something that's proportional to this, if we're trying to find, explore different values for theta, all we need is something proportional. We don't need something exactly that. Okay, so this is the likelihood function up there that was given by this. We just saw that, and this is the prior distribution is given by that. Okay? Okay. So great. We formulated the key things we have to bring to the table. Prior. We have our likelihood function. And that gives us, through the magic of Bayes' rule, the posterior. Now, let the magic of Markov chain production occur. Now, how does this occur? Well, I'm not going to go into all the theory behind it, but the idea here is that that if we want to, so if we have an arbitrary function, folks, suppose I told one of you, I have a probability distribution. Maybe it's a beta distribution. Maybe it's a Cauchy distribution. Maybe it's a Gombert's or what have you. Some distribution. And I said, I want to draw values from it. I want to sample from it. I want to draw values that are distributed according to it. So, maybe it's a log normal, and I want to draw values that are log normally distributed. So there's more of them drawn from here and fewer, out here. They tend to cluster here. If I want to take an arbitrary distribution and I want to draw values from it, how do I do that? Well, it's fairly simple if you have just one dimension. It's in one dimension. You compute what's called a cumulative distribution function. If you could draw a uniform value, you could turn it into a value from this distribution. The problem is that as the number of dimensions goes up, that breaks down more and more and more. Moreover, it becomes quite awkward to do this in terms of kind of how big how finely should we compute the CDF, etc. So Markov chain Monte Carlo technique lets us generate samples from theta for an arbitrary distribution without knowing anything about the CDF, without knowing about the cumulative distribution function. Okay, so how does this occur? What we do is we draw a candidate value for theta. Okay, so we draw a value that might be the case. Often this is just a random perturbation around the last one we gave. In other words, if the last one we gave was a certain value, we just drew something in that neighborhood. If it's the very first one we're seeking, we pick a random one as long as it has non-zero chance of occurring. And we then run the simulation model, okay? And this takes significant work. Why do we need to run the simulation model for this candidate value of theta? This value of theta we may be actually emitting. Well, it's because we need to figure out the likelihood function. How likely is it that candidate value will explain the observed data? Now, once we've done that, Now we can compute the posterior. We do that with the likelihood function that we just computed based on the simulation model, and we multiply it times the prior. And then we either accept this new value and emit it, or we report the last one. Okay. So if it's accepted, we take it as a new sample. If it's not accepted, we just stick with the last one. So let's think about this a little bit. Let's think about this a bit. Why does this actually work? Well, if you think about it, let's suppose we're sampling from this distribution here, and our last one was here, right? Maybe we pick, so this is our last value. We're sampling from this distribution, and we last reported that one. So we're going to pick a candidate value that's down here. And we're going to look at the relative probability of that one and this one, and we're going to say, okay, this new one is very unlikely compared to the last one. So it has just a small chance of being accepted. That's how this typically works. And it's based on the ratio of the probabilities of both of them. If it's much less likely, we will typically reject it. Whereas if we had picked a candidate, if we reject that, we stick with this one and re-emit it. And then suppose the next candidate value we pick is over here, for example. That one's more likely, so we're more likely to go to that. And basically, the higher the value of it is, the less and less likely we'll prefer another one to it. Because we're looking at the ratio, okay, between the last one and the current one. And if between the candidate one and the last one, if the candidate one was a very high value of the posterior, we're more likely to stick with it. We're less likely to accept a new candidate because the candidate's value is small compared to that one. On the other hand, if the candidate is higher than the last one, we're more likely to go to it. So we're more likely to stick around ones that have a very high value and to go away from ones that are below that. When it turns out that if you run this thing, you could show, or if you really study it, you can show that you can prove that this is a what's called an equilibrium distribution, a stationary distribution. The posterior distribution is a stationary distribution of it, and it's the only one. So it turns out that this method, which is very simple, involving accepting and rejecting new possible samples based on the relative values, it actually samples from the posterior. It allows you to draw samples from any posterior that you can formulate without formulating the cumulative distribution function. It just allows you to say, I want to draw values from posterior like this and to sample from it. So what's the basic amount of computational effort here? Well, typically we will be running a simulation model a large number of times, and it's not untypical to run it hundreds of thousands of times. Okay, you're generating these sample possible candidate values, and whether you reject it or accept it depends on the value of the simulation model. So you have to run it just to determine that, and you have to run it many, many times. So typically you run through a burn-in period, which could itself be 10,000 runs or 100,000 runs, and then you're believed to be in a pretty good situation to start generating representative numbers. It's kind of forgotten whatever original state you gave it, and it's probably sampling pretty well from the distribution. Okay. It's notable that not much of this work can be done in parallel, but if you have multiple walkers that sort of explore the space, wandering around, you can run them in parallel. Okay, so how do we do this? Well, we have this R-Vensim library that I wrote that basically permits R to call off to Vensim to evaluate a model. Okay, and then we can read the values from the Vensim model and assess the likelihood function. And in this case, you do 100,000 MCMC iterations following 20,000 burn-ins. And we examined this for two SEIR scenarios, one for a baseline scenario, one for a hygienic intervention scenario. Okay? So this is kind of what we got out. First of all, we examined the impact of this prior. suppose our prior is off. So what I'm showing here is a what's called a hex bin plot, and it shows sort of the relative values associated with the posterior for different values of C and of P here, right? So it's where it's darker, it's more peaked. So this is kind of a peak here. So this distribution is actually reasonably normally distributed, multivariate normally distributed. You sort of see this peak, it's like Mount Fuji, right? And sort of peaks up here in the middle. And what it's telling us is that, you know, in the grand scheme of things, you could have a value of C between about 1.85 and 10.25. It's pretty tight there. And P between about 0.76 and about 0.8, almost 0.86. And it's clustered in the middle. Now, this is when we assumed a prior that was terribly off, horribly misleading prior. And you can see there's almost no difference between the two. What this is telling us is the prior influences things, but at some point the amount of data overwhelms the prior. It overwhelms your original prejudices, and you say, look, this is the message is coming through here, that even though I originally thought that, you know, the values were much more likely to lie in this area, theta, of C and P, in other words, of theta, were more likely to lie off here or something. I can't remember what this prior was, but it was way off. Even though I thought that this was very unlikely, eventually the empirical data pushed it inevitably to say, okay, this is the most likely values of C and P we have. So it's quite robust to the prior here. In other words, we have enough data to make us reasonably confident of what the data is telling us. We're not knocked about by the varied assumptions for the prior. Okay, so when we have this distribution, what can we do with it now? So we have this distribution of C and P. Why is that any good? I mean, what can we do with it? Well, one thing we can do is we can actually create distributions over time. Okay? So here's the model over time, and we can look at, for example, the count of exposed individuals, a latent variable model. We don't have direct data related to that. But from those samples of C and P, we can run it, drawing values from that distribution, those samples from that distribution. We can then sample the distribution for each of these time points of the number of exposed individuals. How do we do this? Well, for each of these time points, for each value of C and P, we ran the model, simulation model. C is the only one that matters, the simulation model itself. And then we plotted out the number of exposed individuals at each time point. And we did that for different values of C and P, and that led to histograms. For each of these points of time, there's kind of a histogram. This one peaks in the center and goes down. This one peaks in the center here and goes down. So we have these distributions. And what we see is that, they're quite tight down here. They're quite broad up here in terms of variability in the number of exposed individuals posited by the simulation model in light of these distributions of C and P. Okay? So we can take those samples that we got out. This is something that emerged directly. I'm just plotting things that came out directly from the Mcmc process. This is feeding them into the simulation modeling and seeing what comes out in terms of output. And I would note that we could very readily create credibility intervals here. What are the intervals for time 20 within which 95% of the values lie here? Trying to do that based on conventional calibration results, even if you have confidence intervals of C and P, is a fool's errand in a nonlinear model. Okay. Moreover, we could take the difference between two scenarios and output for two scenarios. So here's difference. I chose a different outcome measure. Difference in effective individuals between an intervention and a baseline case for different points of time. So in one case, we lower beta, and the other case we leave beta constant. And the question is sort of what's what's the difference between intervention minus baseline in terms of infective individuals? Well, the intervention has fewer infective individuals early on, but the infection does spread, and so later you have more infective individuals, and once again, for every point in time, you have distributions here. Distributions implied by, derived from the, and derivative to the values that we drew out of the simulation model, drew out of the Markov chain Monte Carlo process. So in other words, given our 100,000 samples of CNP, we can just put this into the simulation model, take the difference, and boom, we're done. Okay, now you can view this at a certain high level. You can view this whole process as leading to almost a combination of things that we often separate in the modeling process into calibration on the one hand and sensitivity analysis on the other. Here we're actually getting out of a process that's kind of like calibration. We're actually getting out something that gives us a sense of sensitivity of the model. How uncertain are we? How sensitive is the model to different values associated with CNP? And we can examine at different points in time, for example, how sensitive are model outputs with respect to these values for CNP. You notice here it's quite insensitive. The values are pretty clear where this will lie no matter what your value of CNP is. Same thing early on. It's really in the central place that it's uncertain. Okay. So what's the role of the simulation model here? Well, the role of the simulation model is, it helps us compute the likelihood function. It helps us project the consequences of our parameter assumptions concerning C, in this case, in terms of outputs that would help us assess the plausibility that those parameters yielded that empirical data we've seen. Okay. Here we are assuming, okay, there's a certain simulation model. Again, we could, in principle, use more sophisticated versions of this to choose to assess probabilities of certain simulation models. What are some practical concerns associated with this? Well, the burn-in time. We need to run this thing through a burn-in period of, say, 20,000 iterations. And there's ways of judging whether it's reached appropriate burn-in, whether it's well mixed now. And secondly, and this is where a lot of my time has been spent using these methods, adjusting the step size in this random walk which occurs in picking candidate values to so that we have a good, what's called acceptance rate, a good rate of acceptance of possible candidates. So in other words, we want something that's going to explore the space well, but it's not going to be so aggressive. It's always rejecting it. If we, ironically, if we either explore it too aggressively, we're going to be getting a lot of values, posterior values that are very, very low. So almost never accept that. So if we choose values that are way out there, we'll almost never accept them. If we choose values that are too small a difference, we'll almost always accept them, but we won't go very far. In either case, we don't explore well. And so we need a kind of level of acceptance, and we have to tune our Mcmc algorithm to give us that nice level of exploration of the space. And there's a good literature on there. There's other issues. If you're doing this with lots of parameters, sometimes you'll find that it's highly dependent on a relationship between parameters. So if there's this high dependence between parameters, I'll go back and look at an earlier slide here. Here, if you have this high dependence between parameters, it has to kind of walk this tightrope. And if it goes off on either side, it falls off, and it probably won't accept it. So it often has very slow exploration of the space because it just has to, by dumb luck, find its way along this tightrope. Whereas if you have a situation that's more like this, it can explore lots of places and still get a decent chance of acceptance. And so it explores with a higher acceptance rate. Right, and there's some desirability for transforming the parameters so you can operate in unbounded space. You're not butting your head against the edge of the space. I'm going to drop the thinning rate stuff, which turned out to be often is not needed. And there are ways of assessing if you've gone far enough to get good sampling. What I'll say is we make use of a very simple algorithm, one based on random walk Monte Carlo, and I'm glad to share it with people. It works with Benson, as I said. But in R, there's many different MCMC algorithms that have been explored. Random walk Metropolis Hastings, or MH algorithm, is particularly simple and very commonly used, but you can go to town with more sophisticated algorithms to enhance acceptance rates, etc. A broader perspective on this before I finish up here in just another few minutes. MCMC is one type of Monte Carlo algorithm. What we saw yesterday, particle filtering, is a different sort of algorithm, and they fit in the space in different ways. Broadly speaking, crudely, as I see it, this sort of MCMC works really well if you have a deterministic model. But it works really well specifically for estimating parameter values. Okay? It's not going to give you correct your estimates. If you've been running the model, it's not going to correct your estimates of the current situation right now when new data comes in. Rather, it's going to be used to estimate different values of parameters. By contrast, the particle filtering we saw yesterday it basically can be used for parameters, but it basically gives you an update to your current estimate of where you're at right now. And that's very useful sometimes to kind of reground your current understanding of the current situation. Particle filtering is a recursive algorithm, so when a new data point comes in, you're going to have to reconsider all the data points. You just use the results from the previous one, whereas MCMC, if you want to do each time a new data point comes in to run MCMC, you'd be running on all the data points. So it's a so-called batch algorithm. It's an offline algorithm. It's not running live, so to speak, whereas SMC runs live. Okay. Okay, just conclusions. MCMC provides a more general alternative to traditional calibration. It allows for deriving posterior distributions and sampling from them, sampling from these posterior distributions. And you can, what's really nice from my mind is that you can define this likelihood function, which explicitly gives a probabilistic model in MCMC. It permits greater robustness in model conclusions, and in fact, in choosing between models if you use it in a more sophisticated fashion. Using our software framework, we have very nice support that R provides in various packages, which can be leveraged together with system dynamics modeling. But I would note the latest version of Benson also supports MCMC, although its support for assessing convergence and convergence diagnostics falls somewhat short of what you'd like to see. It's also recommended that you look at that if you think about applying it, because it can all be done in that package. Okay, so those are all my comments on MCMC. Let me know, my thought was to go on now to talk a little bit about